All right, guys. So let's assume that we have k degrees, k vertices such that they are leaves in graph G with n vertices. And we have a maximum degree, we have a max degree, a vertex with highest degree D. So we know that like the summation of the degrees are we can show D1, D plus 2, D, D like Dn. So we've got n vertices here, and it is equal to, should be bigger than D. Okay, and let's assume that we've got k leaves, and this is like k leaves and one vertex with degree D, and let the rest are degree 2. So here we will have 2 times n minus k minus 1. All right. So can I write this one like here? So I can write this one here. So this will be equal to 2 times n minus 1. So it comes from this parenthesis here. And this one will be minus plus t plus 2. Actually 2k plus k. So this will be the only simplification we can do is just t minus k. Okay. On the contrary, the graph G, oh, actually just t. Okay, it should be here t. Okay. We got n vertices, so you got n minus edges. So we have 2 times n minus 1 degree. Okay. So from here, from the summation of degree, which is not less than this guy, we will have 2 times n minus 1 bigger than 2 times n minus 1 plus d minus k. So we can cancel these two positive animals. So we will have k bigger than d. So this means we have proved that the number of leaves is bigger than the number of the maximum degree of a vertex in graph T. All right. Let's do now this question. So this question, it has a explanation in a box. Recall that any graph with any vertices has degree sequences. Okay, and let's call them D1, D2, Tn. And we can follow the convention at this course that we will list them from large to smallest. So for example, if we have a vertices A, B, C, D, and E, with these vertices, with these edges, so we will have B, we got C, got D. So this one has 3, and the rest has got degree 1. So the question, two non-isomorphic trees with the same degree sequences. So this means we can have we can have like this guy. Two same sequences. So let's add this one here. The other one. This is the famous. These two are the famous examples. Okay, same vertices. So let's add this one to here. So we can see that same degree sequences, but they are not isomorphism. But these two trees are not isomorphic because the structure has not been preserved. Okay, so the reason is like you can know that. So because here, for example, you have uh, three vertices of degree 2, but here in this one you have 4 vertices of degree 2. So that can be one reason. So they are adjacent together. So yeah. All right. So 4 adjacent degree 2 vertices, 3 adjacent degree 2 vertices. Okay, which they are not the same. So the structure of the edges has not been preserved. So they are not isomorphic. All right, a rooted tree is a tree with one distinguished vertex called root. So we will write it as like this one, this one. So this one, this one. So this guy is the root. In a root tree, the distance from any vertex v to the root is the level. So this guy has level 1. Level 1 is, this is level 1. Okay, this guy has level 2. Okay. In a rooted tree with vertex v at level k, okay, the vertices that are adjacent to v at level k plus 1. So this is k plus 1, which is 1 plus 1, 2, and this one is 1. So this vertex is the child of this vertex, and this one is parent of this vertex. So the siblings can be defined accordingly. The depth of a rooted tree is like the depth or height of a tree is the maximum level. So from this tree, the depth or maximum level is 2 because the longest distance is from 1 to. And associated with any rooted tree is the directed root tree given by making all edges be arcs pointing from the parent to the child. So this can be obtained like this, this, this. All right, so let's do this question. So I can see that in this question, R, E, H, D, J, S. So I can see that I should remove this one. Okay. M, D, and this guy. S has just S is this one. So that's right. So we see that how many children does it have? So we see that just two. All right. How many vertices are there at level 2? We can see that the part B, yes, it's possible to find it. What is the parent of M? Okay. How many descendants does E have in this tree? So it is this one. So descendant of this M, how many descendants does E have in this tree? So it can be S, D, M. Okay. All right. So I was just confused. Descendant of R, not R, just E. So S, C, M. That's why. All right. So this question is okay. You can do it completely by yourself. Ordered tree is this guy. It's a special kind of the or rooted tree in which the children of a vertex are ordered from the left to right. So it's important to put it in a chart in left or right. So it will be important from now. A binary tree is a special kind of ordered tree in which each vertex has at most two children. Okay, at most two children. So now, if there are two children, they are distinguished as left child, right child. Furthermore, even if there is only one child of a vertex, that child is designated as either a left child or right child. All right. A full binary tree is a special case of a binary tree in which each vertex has either 0 or 2. All right. So now, so consider the rooted tree in question 7. Make T into an ordered tree using left to right from the adjacency listing. Who are the first and who are the second children of H, and who is the first? So you will have a look at here, and you can do question 8 as well. Okay, so it is okay. Make the tree part A into a binary tree by defining first children to be left children. So this question is okay, and you can do this question. So C is the tree in part, make the tree part A into a binary tree by defining all first children to the left children and the second children to the right children. So you can have a look at this guy, this tree, and you can say that is it full binary or not. All right, question 9. Let's have a look at this one. All right, so T1 we will have T2 and we will have T3. So T1 and T2 are isomorphic. So define three ordered trees, T1, T2, T3, with orders consistent with T1, T2 are isomorphic as rooted tree, but not as ordered. Not as ordered tree. Okay, what was the ordered one? Ordered one as the special kind of that left and right children, they are important. Okay. So for this one, yeah, this B, C, B, D, E, and C, F. Okay. And so this is the T1, and we wanna draw a T2 or create T2 are which are isomorphic as rooted tree, but they are not ordered trees. So I can sketch this one. X, Y, Z. Can I move this one to down? X, Y, Z. Y can be, let's make it U, and Z is V, W. So obviously isomorphic, but they are not ordered because the order X has this order. So X has got two grandchildren from the right in the right, which is this one has got this one here. So this graph might be important, like look, it looks the same, but since the order is important, so they are different. They are not equal in terms of the order, but definitely are isomorphic. So T1, T3, so the other one is T1 and T3 are isomorphic as trees, but not isomorphic as rooted trees. So T1 and T3, they are isomorphic as trees, but not isomorphic. All right. So when it comes to my mind, T3. So let's see that I can do this. M, N, O, and O, P, Q. All right. So this one definitely not isomorphic. So T1 not isomorphic with T3. Okay, but as 3, yes, as um, the rooted one, so as 3, okay, isomorphic T1, okay, so because T1 and T3 isomorphic, so because this guy is FCA, FCA, okay, O here, P, Q, D, E. So as 3, they are isomorphic, but definitely as rooted tree, they are not isomorphic because it's just obvious because this one has F, this one doesn't have any child. Yeah, and this one has like grandchildren, this L, but this A doesn't have. All right, that's right. Okay. Now, question 10 is about the Hoffman, and as we also worked about this Hoffman question in the class. Okay, so you can read this one here. Okay, so it's interesting a little bit. Now, I need to write it here. Do you see that? So 1, 0. So I just copy this one to here. So 1, 0, 1, 0. Okay, 1, 0, 1. Okay, this one is G. Now, the other one is this guy, this guy, this guy. O. The other one is again 0. As a result, this one is O. And the other one is this guy here. So I will write it here. I will write it here. So let's try to use another color. Okay. 1, 1. It means good. Now let's use another color if I have. So, okay, I don't want to use another color. So again, the same thing. So what was it? Okay. 1, 1. B. So the other one should be this guy here, 0, 0, 1. Okay, so it is like this one. So let's write 1, 0, 0, 1. So 1, 0, 0, 1. So this will be E. Okay, so this is this one. So the other one is this one, definitely. Okay, it should finish with 1 if it starts with 1. So this is the last one I do for you. So I finish the colors. So 1, 0, 0, 0. Oops, not 1, 1, 0, third 0, 1. So it should be this. Okay, so you can do the rest and the half macro. All right, so part B, use the same tree to encode the word done. So if I do this one, D was easy, 1, 1. Okay, so I see that 1, 1. So the other one, O, is 0. The other one, N, I can do this. 1, 1, 0, 0, 0, 0, 4 zeros and 1. So 1, 0, 0, 0, 0, 1. And what's the E? It should start with 1, O, O, E. So 1, O, O, 1. So D, O, N, E. Okay, Is there any strings that? So yeah, of course. So there are strings that. So Hoffman code, it's not corresponding um, um, with all the possible strings. It means it's not onto function. Okay. For example, 10, 1, 1, 0 is a string, but not corresponding to any letter. 1 is also, and 100 is also another example. Okay, this is until question 10. I will continue with the next video with the rest of the questions.